Welcome to reInvent. My name is Luke Youngblood, and I'm here today with Greg Femick. And we're here to talk to you about how to build a serverless pipeline to transcode a 2-hour video in minutes. So I'm really excited to share this with you. I think it's a fun presentation. We're going to save a little bit of time at the end for questions, but during the presentation, we won't be taking any questions, but we'll save a few minutes at the end. So let's go ahead and get started today. This is what we're going to cover today. First, I'm just going to give a brief overview of serverless technology. I know everyone in the room here, this is a 300-level session, so everyone pretty much knows what serverless is, but I'm going to just give you a quick reminder, recap. And then I'm going to introduce the challenges. I'll introduce Greg, and he'll talk about the challenges they faced and how they built the serverless transcoding pipeline. He's going to talk about some of the lessons learned that can hopefully help you if you have a similar use case, and then give you some best practices and recommendations for serverless, especially in media and entertainment use cases. So let's talk about serverless. What does serverless mean? First of all, of course, no servers to provision or manage. We take care of the undifferentiated heavy lifting for you. And then also it scales with your usage, right? You can launch a single Lambda function, or you can launch 1,000 Lambda functions. So you get this very elastic and scalable serverless technology. In addition, you never have to pay for idle. So this is a big selling point for a lot of our customers that are managing compute on EC2 today. It's very rare that we see customers that have 100% CPU utilization on their EC2. But with serverless, you only pay for the exact amount of compute that you consume. And so you never have to pay for that excess idle capacity. Of course, availability and fault tolerance are built in to the platform. And so let's just talk about what a serverless application looks like briefly. So you've got an event source. Serverless applications tend to be event-driven architectures, right? So that event could be a change in a data source, like someone has uploaded an object to an S3 bucket. It could be a request to an API gateway endpoint. It could be a change in a resource state. Maybe AWS config, notice that you made a configuration change on one of your cloud resources. So you can launch a function in response to events. That function can be Node, JavaScript, Python, Java, C#. And then you can use that Lambda function to do anything you could do in code today. So you can talk to other AWS services. You can talk to third-party partner services. Pretty much anything you can codify can be put into a serverless function. So what are the common use cases that we see customers using? First of all, static websites, very popular use case. Customers are storing their static website in S3, and then they're building these rich, dynamic applications, these complex web applications that talk to serverless backends through API gateway. So customers are building these backends for mobile, for IoT devices, for desktop, for any type of client you can think of. And then the use case we're going to talk about today is really this one on the third from the left here, the data processing use case. So customers are processing data in real time, but they're also using an interesting pattern, which is kind of comes from the Hadoop ecosystem called MapReduce. So if you're not familiar with MapReduce, what it is basically you have a function that maps your workload. So you take this large compute workload and you map it across multiple parallel processes. So by parallelizing your application, you can actually process data much quicker than you could if you had a single process handling that. And then at the end, you have to reduce the outputs of all those mappers into the single output that you wanted. So for use cases like transcoding video, it's actually very powerful because now I can run this in parallel across hundreds or thousands of Lambda functions. And that's what Greg's going to talk to you about. So I'm excited to have him share that with you. We also see customers using serverless for chatbots. They're using Amazon Lex to power chatbots. And they're building these rich conversational interfaces, things like booking a flight, booking a hotel, ordering a pizza. And then once they understand the intent of what the customer is trying to purchase or to book, then you can hand that off to a Lambda function that goes ahead and fulfills that request for the customer. So we see customers integrating serverless into their Alexa skills. This is a very popular platform for Alexa. And then the last use case we really see is IT automation. Many of our customers are using serverless technologies to automate their IT infrastructure in the cloud and even on premises. So that's things like a policy enforcement, making sure your systems are secure, extending AWS services, lifecycle management. This is a very powerful use case. So with that, I just wanted to go ahead and introduce Greg. Greg, why don't you go ahead and tell us a little bit about yourself?
Thanks, Luke. So I'm a software developer at Revel. We're a small team in San Francisco with a passion for video. We come from a number of different companies like Hulu and Netflix and Amazon, but right now we're focused on building a next generation television experience for Verizon. So what I'm going to be talking about today is the way we've used Lambda in our video processing pipeline. So to set the stage a little bit, I'll tell you some of the challenges that we ran into when building our video-on-demand video pipeline. So we have a lot of videos to transcode, and they come from a variety of different sources in unpredictable ways. So we support direct browser upload, FTP, Aspera. Sometimes we literally get a hard drive in the mail with several terabytes of videos to process. But basically, we don't really know exactly when this is coming. And the input files themselves can vary from like a small clip someone captured on their cell phone to a full-length feature film from a major studio. So we have a wide range of input formats that we need to support as well. Now, after we take the videos in from the content owners, we process them to be displayed on a variety of different devices. So this is just a quick list of some of the formats that were produced. Obviously, you have standard progressive MP4s, and then HLS and Dash for iOS and Android. And we also, based on a variety of contracts, have DRM requirements too for some of these outputs. So our early solutions included some popular software as a service solutions. We ran into a few issues with these. The first was that coming from lots of video backgrounds, we wanted more control over the process eventually. And also at scale, we found it wasn't particularly cost-effective. In particular, the marginal cost of producing additional output formats after already we'd transcoded one variety wasn't quite what we thought it could be. So our initial approach was to build a transcode farm on EC2. Pretty straightforward here. It solved the control issue and the cost concern to some extent, but created some operational challenges. So get a little more in detail of that. So we had people using the service who would take a quick video on their cell phone and upload it and want to be able to share it very quickly. So we wanted to avoid any queuing where their video would be stuck in a long processing queue for a while. So that means that we wanted to be able to pretty quickly respond to new demand, but we had a cold start problem. Once you combine the cost of starting the instance, downloading our software, installing any updates, downloading the file to start with, it would be a significant amount of time between the need for extra capacity arose and we were actually had that capacity spinning away and processing the files. And then we had a problem on the reverse side too when it came time to scale down. So if we had a large instance that was capable of running multiple jobs, but there was a single long-running job on it, an HD video transcode, at least at our settings and with the way we had it configured, could take several hours, there's no way to really reuse that extra capacity that's on that instance. If it can process 5 jobs, but you only have one running on it, you can't really stop the job in the middle and move it over to another machine to reclaim that excess capacity. So we had wasted capacity there. And then when we built this, there was also a 1 hour minimum, or like you were build an EC2 in 1 hour chunks. So that meant that if we spun up a bunch of instances to process videos for like 20 minutes, you'd pay for the rest of the hour anyways. Since September, this is now improved, but it's useful at least for motivation as to why we did this in the first place. So why did we pick serverless for this problem? It solves our cold start straight away. So we don't have any issues with starting machines or installing updates or waiting for them to join your work group and get started, ready to go right from the get-go. No wasted capacity. Luke touched on this before, but we can scale up and scale down fearlessly. And then all of this just results in fewer operations challenges for us. So our code runs the same whether we're running on 2,000 cores or 20 cores. And as I just mentioned, it's the large standby capacity that is critical for us here. So our current limit is 2,000 concurrent functions, but that's not like a hard ceiling there. And I'll get into this a little bit more in detail, but the way we mapped the problem to solve it in a serverless standpoint means that we have flexible resource allocation. So we can decide, hey, we're going to put a lot more resources against solving this particular problem, transcoding this particular video, because it's more important. And that can actually change throughout the job. So if we're halfway through processing a large file that's sort of a background task, and we get a new file that we need to process, put more resources against immediately, we can do that with this approach. So here are some of the challenges of taking video transcoding and mapping it to a serverless world. We start with big input files. So some of our files are hundreds of gigabytes, and we don't really want to have to wait to download the entire file before we start processing it. And in Lambda's case, there's not even enough space to download it in the first place. So the other thing that makes this big file problem tricky is that most of the video processing tools aren't set up to handle their input and output in chunks. They basically assume that you have the whole input file on disk somewhere, and they're going to be writing the whole output file to another spot on disk. So they're a little bit difficult to stream that. And the jobs themselves can be slow. Like as I mentioned, it kind of depends on what settings you're using and your quality ratios and whatnot. But an HD transcode of a movie can take several hours. And these jobs are sort of hard to pause and resume. Most of the tools don't support serializing their state and uploading it to another machine and starting it fresh from there. So here was our plan. Basically, when you come up with a problem that you can't solve straightforward, what do? You divide and conquer. So as Luke mentioned, this is MapReduce here. So a basic idea is that we'll consider the video in small chunks. We used 5 seconds, but that's just a number we picked. And we'll transcode each one of those 5 chunks in the map step. And then when we need to produce an output like a progressive MP4 for the whole video, that's where the reduce comes in. We'll reduce all those small chunks to form the resulting MP4. For some HLS cases, we can actually use the output of the map step directly. Like the output of the map step is the TS segments that you want to stream. But for other cases, we have to do some post-processing there, in particular DRM. So here are the tools that we use to build this. Of course, we're here because we're using Lambda. The big components of this are the instant scale that we get and just the huge parallel compute capacity. S3 was also a critical part. So in particular, multi-part uploads, which let us create a large object in S3 without having to have the whole data buffered on disk at some point. We don't even have to know how big it is when we start. We can just start throwing data into S3, and at the end we'll say, OK, that's all I have, and it'll create the object for us. And the other important part was range requests. So this is sort of the reverse, and we don't have to have the whole file to upload. We also don't have to download the whole file at once. We can just ask for a small part of this large input file to process. To do the actual video processing, we used ffmpeg, mostly for its wide range of features, in particular input and output formats. And for our language of choice, we picked Python. It's natively supported by Lambda, and also the team at Revel has a lot of experience with Python, so we felt comfortable using it to stick together all the C code that does the actual work. So here's the architectural diagram, which I'll go over briefly here, but then we'll dive into bits in more detail as we go. So all of our files start in S3. We take them from the various upload locations and dump them off in S3. And then we run our map. So critically here, we can run basically an arbitrary number of these maps in parallel. So taking each 5-second chunk of the video and processing it doesn't depend on any of the other 5-second chunks. So depending on how many cores we have available or concurrent Lambda function executions, we can run a bunch of these all at once. The results, those TS chunks, end up being stored in another S3 bucket. And then we'll run our reduce steps on those chunks. So there's a simple reduce to combine them into an MP4 file. More complicated reductions to produce DRM outputs, and for this example, we'll go over what we do for HLS, and similarly for dash DRM files as well. So let's dive in a bit to our map step. So this is the what I'll call the chunk function, because we produce a TS chunk from it. So what we must do here is decode a small portion of the input file, transcode it to the desired bit rate, and then upload that chunk to S3. So the challenge here is actually decoding that small chunk. Because, as I mentioned before, we have large input files, and we don't want to have to download the whole thing. Now, ffmpeg does most of the work here for us, because they support an HTTP input, so they'll only ask for, via HTTP range requests, they'll only ask for the small bit of the files they need to process. But unfortunately, what we've found out is that ffmpeg will want to like read a few bytes and then seek forward and then read a few more bytes and then seek backward or whatnot. And all of these little requests for a byte or two end up being separate HTTP requests. And the overhead of all these HTTP requests ends up being too expensive. So what we did is we built a cache that runs in the Lambda function alongside Lambda. Just an HTTP daemon there, and what it does is it proxies all the read requests from ffmpeg to S3. So what we do is we fetch the files from S3 in larger chunks than ffmpeg will ask for. So when ffmpeg is slowly moving along or moving backwards or reading the same part, there's a good chance that we actually have that data already in memory. We don't have to make a separate HTTP request to S3 to fulfill that. And the other thing that we do is, because even though it'll kind of move around a little bit locally as it's processing, the general trend is still sort of from the beginning of the file to the end of the file. So we'll actually proactively fetch the next chunk of the video while ffmpeg is processing the previous chunks. Basically, you never want your CPU waiting for your I/O or vice versa. So I'll talk a little bit about some of the problems we ran into running ffmpeg inside a Lambda environment. This hopefully won't just be specific to ffmpeg, and you could apply this for any other binary that you might want to run. So we found that it was unreliable if dynamically linked. So we ended up statically linking everything. Obviously, much larger binaries, but it still fit well within the Lambda limits. There's actually a lot of space there, particularly if you use the S3 upload as opposed to like trying to do it from the browser. And I'll also talk about some of the things we ran into with running ffmpeg in particular. So obviously, if you're doing multiprocessing in a Linux environment, you're probably talking about forking. And when you fork the process, you inherit everything from the parent process. What you might not realize is that in Lambda, that parent process that you're running actually includes some of the Lambda sandbox that you're running your code in. So in our particular case, what we found is that when we forked ffmpeg from our Python code, it had inherited a few file descriptors from the Lambda sandbox, in particular standard in. And we got standard in input that we weren't expecting, which caused a few bugs from time to time. We obviously just fixed it by ignoring standard in. You could close your file descriptors. But just be aware that if you're running multiprocessing in Lambda, you might end up with things in your fork process that you didn't manually create yourself. And also, I'll talk about this in more detail, but if you're running multiple Lambda functions back to back, there's a chance that it reuses the containers, which means that if you didn't clean up a process that you started in a previous Lambda execution, it might persist to a subsequent one. So make sure that you always clean up your process when you're done, including error cases. That was obviously the one we missed. So now I'll talk about one of the reduced steps. So after we've mapped our large input file into a bunch of small chunks and transcode them individually, we'll reduce them. And one of the main ones is to produce a single MP4 file for distribution here. So the basic idea here is we'll read in the TS chunks, combine them into the MP4 file, and upload to S3. So the challenge here is on the opposite side. It's the output file which is too big, as opposed to the little input files. So there's not enough space to store it in the temporary storage for Lambda. But ffmpeg, again, meets us halfway here, because they support FTP output. But the challenge here is that for the kind of MP4 files we're producing, after writing most of the video content, ffmpeg wants to seek back to the beginning of the file and insert some additional data, essentially like bookkeeping, location of iframes for seek points and whatnot. But obviously, this creates a problem if we were planning to just like upload the data as soon as it arrived and not store it around, because how do we shift everything down to make space for it? So this is where our S3 multipart upload comes in. So what we did is we built a FTP like adapter, which runs inside the Lambda function, so the way our cache ran inside the Lambda function. And it adapts FTP input to an S3 multipart upload. And then what we do to handle this seek back to the beginning and write some additional data problem is we delay uploading the first chunk. So one of the features of a multi-part upload is that you don't have to upload all the parts in sequence. You can give them numbers and start with 2, and then at the very end come back and say, oh, by the way, here's part 1. And all your parts don't have to be the same size either. So if you don't know how big part 1 is because you're not sure what ffmpeg is going to go back and write, you can just wait until the very end until you know. So that's what we do here. Now ffmpeg will dutifully attempt to shift all the data down after it's gone back to the beginning and wrote, but in this case we can just lie and just say, hey, yeah, here's some data, and it parrots it back to us and it works. So here's another of the reduce functions we do. So this is in particularly for producing DRM output for HLS. So we read in our TS chunks, which we produce from the map statement, from the map functions, and then we combine them and encrypt them, and then upload the encrypted file to S3. We combine them for cache efficiency, just so that the CDN only has one object with a HLS byte range playlist. So the challenge here was around the time it took for this function to execute. So our other reductions would happen in a single, Lambda function, our 5-minute limit, just fine. But in this particular case, the sample AES encryption, involves repackaging the TS stream, and it would take too long if for some of the longer movies it wouldn't finish within a single 5-minute function. So what we ended up doing here was just daisy chaining a few Lambda functions together. So if the first function didn't finish the multipod upload, it could actually serialize the state of the multipod upload, pass that along to a subsequent Lambda function, which would resume the multipod upload and continue encrypting and concatenating chunks. So this worked pretty well. Just one thing I'll mention here, you may find that, in fact, I expect you'll find that your download and upload speeds aren't necessarily symmetric. So make sure that you have some way of restricting download speeds if your upload becomes the bottleneck, because we had a few cases where we ran out of memory just because we downloaded so much that we couldn't upload it all in time. So just have some back pressure there if you end up doing similar streaming processing. So I'll go into our deployment and some of our integration pipeline a bit here. So we build all of our Lambda functions inside Docker containers, mostly just for reproducibility, and so it's easier for developers on different platforms to all come up with the same result. And both git SHA and hash of the script that we use to build the function in the first place end up being included in the name of the zip file we generate. This is our way of attempting to get closer to an immutable build concept. And then once we have this new zip that we're ready to upload to Lambda, we actually don't immediately replace the current version that's running in production. We create a new version of the Lambda function, which is fully functional. We can run tests against it, and we do, to make sure that we included everything we're supposed to include. It's a good binary, whatnot. We didn't introduce any new regressions or something. And then once we're ready and we're confident that function is good to go, we update the alias that we've used in production to point to this new version, and that's actually when the new code starts being run in production. So a little aside here, maybe a little preachy, but one of the nice things about serverless architecture is it makes you divide your code into small sections with well-defined APIs, which is kind of what you have to do to make it testable in the first place. So if you're doing a serverless architecture, definitely take advantage of the fact that your code is now split up in a nice way for testing. So some just general learnings from Lambda that we came through while doing this. I mentioned this before briefly around multiprocessing, but reusing containers can create a few additional challenges as well. So in addition to not cleaning up extra processes that you might have left over if Lambda decides to reuse a container, you might also, if you use any of the temporary disk space, it doesn't clear that for you, so make sure that you clean up that when you're done. Same thing with memory. So the biggest thing here is if you have a process that's eating up a bunch of memory too, but depending on what kind of language you're using, if it's some garbage collected language and created a bunch of big objects in memory, you might run into problems if you run a bunch of functions back to back with cumulative memory usage. And then the last thing I'll mention is that we, obviously with the S3 cache and the FTP adapter, we ended up binding to ports. And so make sure that if you're binding to a static port, that you release that socket before the program ends. Or in our case, we just let the OS pick a socket randomly so that we didn't have to deal with that, but either way. So if you're doing multiprocessing in Lambda and it's not working or you're running into bugs, the sandbox actually has a bunch of common Linux utilities you can just use. So you can spawn PS or top, the logs will show up in CloudWatch, and you can check out what's happening inside your function as if it was a little virtual machine, because it pretty much is. And one last bit here, especially if you have any I/O involved, you're uploading, downloading, doing anything like that, just be aware that your function runtime might be variable. So for us, we'd run into situations where a function would time out in 5 minutes, but we retry it again and it works in 3 or 2 minutes. So just be prepared to retry functions that may occasionally time out. So here are some numbers to go along with these results. So just as sort of proof that it wasn't just a proof of concept, we have 150,000 hours of transcoded video through this system using, well, now well over 400 million Lambda function invocations. So the cost savings, it's a little bit hard to compare apples to apples, but what I'll do is I'll say that if we wanted similar on-demand EC2 capacity, so 2,000 cores of C4 family EC2 capacity, that would cost us about $60K a month for on-demand EC2 instances like that. But we get access to that same scale for an average monthly bill of $6K. Now, obviously, if we transcode a bunch of videos, that'll go up. If we don't, it goes down. But just as a general ballpark for what we're looking at in terms of cost savings there. And then, of course, as the title of the presentation mentioned, because we're only limited in terms of like the time a single map takes, so because we can run a ton of maps in parallel and we have 2,000 cores, we can actually take a 2-hour movie and process each 5-second chunk at the same time. So this means that our time to transcode a full video goes from the time of transcoding the whole thing to just transcoding 5 seconds of it, plus any of the reductions that we need to do. So easily within 10 minutes there, or usually fewer if we put the whole capacity against a single file. So just a few final thoughts that I'll wrap up with in terms of things we learned, things we might do differently. So one of the limitations of this is that you do in fact only have 5 minutes. So if you wanted to do some particularly fancy video processing, or like 4K 60 FPS from a really uncompressed source, you might not have time to do it all within the 5 minutes, depending on your chunk size, of course. And another limitation here, something to be aware of, is that to decode a 5-second chunk in the middle of the video without processing all the previous bytes, you have to be able to efficiently seek. Now we have taken input from a ton of different vendors and major studios to mom and pop shops, and we haven't run into a format yet that we weren't able to do this with. But it's I guess theoretically possible that you'll find a format where you can't just byte range request to the middle and figure out where you are well enough to chop out like a 5-second chunk in the middle. And then, just as a obvious general note, there is a slightly higher cost per CPU hour on Lambda compared directly to EC2. And with our particular approach, there's also some decoding overhead in the sense that each of those map steps, which is producing just a 5-second chunk, has to do some decoding work, which is repeated across. So they all have to sort of figure out, okay, I have 2 streams for audio and 1 stream for video, and do some general decoding of the initial metadata of the file that in theory is a little bit repeated among the different steps. So a little bit of overhead there. So in the future, we'd like to support more output formats. We're sort of eagerly awaiting iOS and Android OS adoption so that we can eventually move to just a single source for both those guys. And better efficiency for small files. What I mean here is just for to simplify the problem for us, we produce 1 TS chunk for each map function we run. But since the function can run for 5 minutes, and when we're doing the smaller bit rates, it takes just a few seconds to produce a 5-second chunk. There's no reason we just have to produce 1 5-second chunk in each map function. So we could save some of that decoding overhead and produce multiple. But that's more of an optimization since Lambda is built down to the 10th of a second. I think doesn't really bite us too much there. Okay, well, thank you. Thank you all for coming today. I think we'll take a few questions.
Yeah, thanks. Yeah. Good job.